Hey everyone, in today's video we're going to be talking about electromagnetic radiation and quantum concept and equations for electromagnetic radiation and Planck's equation. First, we're going to talk about electromagnetic radiation, which is a type of energy that travels through space in the form of waves. And those waves can come from many sources like sun and light bulbs and different things. So light can behave in the form of waves. And light is a type of electromagnetic radiation. So I'm going to draw a light wave like this. And this right here is going to be the midline of the wave. This is going to be the crest. This is also a crest. This is a crest. This is going to be a trough. This is another trough. And the amplitude is the distance from a crest to a waveline or a trough to a midline. And the wavelength is going to be the distance between two crests in a wave, or it can also be between two troughs. Or it can also be like from here to here. Now, the frequency is the number of crests or troughs that pass a point per second. So if there's a higher frequency, then there's more waves per second. Now, a shorter wavelength will mean that there is a higher frequency. And if there is a longer wavelength, that means that there will be a lower frequency. And higher frequency is for like colors like blue and violet, while longer frequency or longer wavelength is for colors like red and orange. So the electromagnetic spectrum is the entire range of electromagnetic radiation. And each radiation types have different wavelengths and frequencies, but the ones with the longest wavelength, and so that would have the lowest energy, to the ones with the shortest wavelength and the highest energy. We would go from starting from the longest wavelength or the lowest energy would be radio waves, microwaves, infrared, visible light, ultraviolet light, X-rays, and finally the one with the shortest wavelength and the highest energy are gamma rays. So now we're going to talk about the quantum concept. So light behaves like a wave, but also has a particle nature. So light can be like a wave particle duality. And light is made up of tiny particles called photons. And each photon is like a packet of energy. And the amount of energy that each photon has depends on the frequency of the light. And the higher the frequency of the light, that means that the photons are going to have more energy. And so, since the photons have more energy, that means that if there's a higher frequency, then the wave has a higher energy. Also, photons have no mass, and they are the smallest pieces or quanta of light. And so you can't divide a photon. Another thing is light energy is quantized. So light energy comes in specific fixed amount, so it's not continuous flow. The quantum concept is that light energy comes in discrete packets, which are those photons. So the quantum concept is that energy comes in fixed amounts or quanta. And for light, the quanta are those photons. And energy does not flow continuously according to this concept. So next we're going to talk about the photoelectric effect. And this happens when light hits a metal surface. It can knock out electrons from that metal, but it only works if light has a high enough frequency. So if it doesn't have a high enough frequency, it won't be able to knock out those electrons from the metal. So if photon energy, which depends on the frequency, is too low, then it can't knock out the electrons out of that metal, no matter how many photons hit that metal. And light behaves like particles or photons with specific energy. And so that confirms that light acts as both a wave and a particle. So that's where that wave particle duality comes from. So now we're going to talk about the atomic emission spectra. And so atoms that have electrons are arranged in different energy levels or shells that are around the nucleus. And so if an atom absorbs energy from like heat or electricity, then the electrons can jump to higher energy levels. And the excited electrons can't stay at those high energy levels for long, so they will drop back to their original lower levels. And as they fall back to those lower levels, they release energy in the form of photons. And the energy and so the frequency and color of that emitted photon depends on the difference between the higher energy level and the lower energy level that it returns to. And so elements have different set of energy levels, and so each one produces a different emission spectrum. And so that is the series of colored lines that correspond to the photon energy. So now we're going to talk about the equation for electromagnetic radiation. So the equation is c equals the wavelength times frequency. C is the speed of light, which is always going to be 3.0 times 10 to the 8th meters per second. And this is constant. So this is the same for all waves. This is the symbol lambda, and this is going to be the wavelength. And it's measured in meters, centimeters, and nanometers. This V is the frequency, and this is measured in hertz or 1/seconds. So now we're going to do a practice problem using this formula. So we're asked to find the wavelength, and we're given the frequency. So we're going to write out this equation. So we want to find the wavelength. So we're going to get the wavelength by itself. So we get the wavelength equals the speed of light over the frequency. Now the problem here is that this is in megahertz, and we want to convert it to hertz. So we're going to do a conversion here. So 1.5 megahertz over 1. Now the prefix modifies the base unit. So mega is 10 to the 6. So we do 10 to the 6 hertz, which is the base unit, over 1 megahertz. The megahertz cancels out, and we're left with 1.5 times 10 to the 6 hertz. So that wavelength equals the speed of light, which is 3.0 times 10 to the 8th meters per second, which is the same always, over the frequency, which is 1.5 times 10 to the 6 hertz. And we're just going to solve this. And we're going to get our answer, which is 200 meters. So now we have another problem. So this time it's asking for the frequency. So we're going to write out the equation, and we're going to get frequency in one side because we're just solving for the frequency. So the frequency is going to be equal to the c over the wavelength. But the problem is that the wavelength is given in nanometers, and we want meters. So we're going to convert that 500 nanometers into meters. The prefix modifies the base unit, so nanometers is 10 to the negative 9, so 10 to the negative 9 meters over 1 nanometer. The nanometers cancel out, and we're left with 5 times 10 to the negative 7 meters. So now we find the frequency. We do frequency equals the speed of light, which is always the same for every wave, 3.0 times 10 to the 8th meters per second, over 5 times 10 to the negative 7 meters. The meters are going to cancel out, and we're going to be left with 6 times 10 to the 14th 1/seconds, or you can say hertz. So now we're going to talk about Planck's equation. So Planck's equation is E equals hv. E is the energy of the photon, and this is in joules. H is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. and V is the frequency, which is measured in hertz or 1/2. So now we're going to do a practice problem. So this question asks for the energy of the photon and it gives us the frequency. So the energy is going to equal Planck's constant, which is 6.626 times 10 to the negative 34 times the frequency which it gives, 5.00 times 10 to the 14th hertz. Oh, and this is joules times seconds. Don't forget the units. And we get our answer to be 3.31 times 10 to the negative 19. And this is going to be in joules. So now we're going to do another practice problem. So this question asks for the frequency and gives the energy of the photon. So we're going to write out the equation and we're going to get frequency on one side by itself. So we're going to divide both sides by h to get the frequency, and the frequency is going to equal the energy over Planck's constant. So the frequency is the energy, which is 3.58 times 10 to the negative 19th joules over Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. The joules are going to cancel out, and we're going to get 5.40 times 10 to the 14th 1/seconds, or you can do hertz. So now we're going to do another practice problem. So this question asks for the energy of this photon, but only gives you the wavelength. So first we're going to want to find the frequency using the electromagnetic radiation equation, which is C equals wavelength times frequency. Because if we use the other equation, then we don't have the energy or the frequency, so we can't use that. So we can use this one to first find the frequency and then use the frequency in Planck's equation to find the energy. So we're going to find the frequency by getting frequency by itself by dividing both sides by the wavelength. So we get frequency equals the speed of light over the wavelength. So the frequency is going to equal the speed of light, which is always 3.0 times 10 to the 8th meters per second over the wavelength of it, which is 4.50 times 10 to the negative 7 meters. And we're going to solve this to find that the frequency equals 6.7 times 10 to the 14th 1/seconds or hertz. And then now that we have the frequency, we can use Planck's equation to find the energy. So Planck's equation is E equals hv, and we want the energy. So E equals Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, times the frequency, which we just found was 6.7 times 10 to the 14th 1/seconds. The seconds are going to cancel out, and we get the energy to be equal to 4.4 times 10 to the negative 19th joules.